going to be video 1 over circles. We're going to discuss chord properties. The first thing we're going to talk about here in circles and chord properties is that the intercepted arc of a central angle has a measure that is what to the central angle. So the arc here from the central angle, remember the central angle has a vertex on the center. So C is the center of the circle. So this ACB is my central angle, and the central angle measure is congruent to the intercepted arc's measure. Notice they're both 80. So the word they're looking for here is congruent. Okay, so the central angle is congruent to the intercepted arc. Okay, we also need to know that the intercepted arc of an inscribed angle, remember the inscribed angle is where the vertex is on the circle, so that would be ADB. And notice it says 40 when the intercepted arc is 80. So it is half the inscribed angle. Okay, or actually that I said that backwards. The arc has a measure that is twice the inscribed angle. Okay, if you worded it the other way, the inscribed angle is half the arc. Okay, so you could put it in reverse and it would be, instead of twice, it would be half. Okay, you also need to know that the chord central angle conjecture, it states that if two chords in a circle are congruent, then they determine two central angles that are blank and therefore two intercepted arcs that are blank. Okay, so we have two congruent chords. What we want to do is draw two central angles from these chords. So T to the center out to U, and R to the center out to S. Now notice these lines ST looks like a segment and RU looks like a segment, and they are because these chords were congruent. Okay, this just means these are two intersecting lines, which means vertical angles are congruent. Okay, so the angles are congruent, and therefore the intercepted arcs are also congruent, because when you have a central angle, it's congruent to the arc. Okay, so if this has one tick mark, the arc would have one tick mark. This is congruent, so this arc is congruent. Okay, so congruent chords make congruent central angles, which make congruent arcs. You also need to know that the perpendicular to a chord conjecture says that the perpendicular from the center of a circle to a chord is the blank of the chord. So if I have this chord AB and I draw a radius, that means from the center to the edge of the circle, that creates a 90-degree angle, it is perpendicular, okay, because that's what 90-degree angle means, and it bisects the chord. Okay, so it is the bisector of the chord. So this radius, when you draw your radius at a 90-degree angle with a chord, you are bisecting it as well, cutting it in half. Okay, the chord distance to center conjecture states that two congruent chords in a circle are blank from the center of the circle. So notice these two red chords are congruent in length. If I were to measure the distance from the radius perpendicular with those, okay, that's going to be an equal distance. Okay, so they are equidistant from the center of the circle. Okay, and that's when we draw them at a 90-degree angle. The perpendicular bisector of a chord conjecture states that the perpendicular bisector of a chord passes through the blank of the circle. Okay, so if you have a chord and you want to be perpendicular to it, and create a 90-degree angle, this pink line must travel through the center. So it has to be a radius or diameter. Alright, so here's two examples. We're going to work with our chord conjectures. In this first example, you're asked to find x, which is this piece here highlighted in green. Okay, we see that this is the center of the circle. Okay, so we have a diameter drawn across. That means if this side is 10, this side would also be 10, because those are both radius. They have to be equal, as is this radius. Okay, that also tells us that this radius must be 10. Okay, so if this piece is 3.3 and the entire radius is 10, that means the unknown piece here is 6.7, and they tell us we have formed a 90-degree angle. Okay, so we can see here that we've created a right triangle and we know two sides. We know the hypotenuse, so we're going to use Pythagorean theorem to solve for x. So remember, when you're doing Pythagorean theorem, if you know c, you're subtracting, so you do 10 squared minus 6.7 squared, which gives us 55.11, and then we have to get rid of the squared on the x by taking the square root. So if you take the square root of that, it gives you approximately 7.4 if we're rounding to the tenths. So that would be about 7.4. And if they had asked you for this side, it would be equal, because remember, if the radius is perpendicular to a chord, it's bisecting it, so those sides are equal. In the second example, they're asking for the measure of arc LN. That's this arc here. We have an inscribed triangle here. We can find this third angle because we know the three angles in a triangle should add to 180. So you add what you know and subtract from 180. So that leaves you with a 65-degree angle. And we know that inscribed angles are half of the intercepted arc. So that this arc LN must be twice 65, which would be 130. Okay, so those are just a couple of ways you could use those chord conjectures.